Alright, so today we're going to be talking about and introducing derivatives. So basically, let's just get right into it. So I think last time we sort of covered that we defined the slope of a curve at, like, let's say we have a function y is equal to um, f of x, right? And then we define the slope of that curve at a point x equals a to be so slope is equal to limit as h tends to 0 f of a plus h minus f of a divided by h, right? And basically, whenever this slope exists, that is known as the derivative of function f at point A, right? And then, so this is at a specific point. If we were to find an equation for the derivative for all points x, right, what would happen is we would get f prime of x, and this prime notation just indicates that it's the derivative of the function f. So f prime of x is basically equal to the limit as h tends to 0, f of x plus h minus f of x divided by h. So notice how these two equations are very similar. We just switched the a with the x, and that's because the top equation is the derivative of function at point x equals a, and then this is just a general equation for the derivative function for all values x where the derivative exists, right? And for more definitions, the domain, so the domain of f prime of x, again the prime indicates derivative of f, is basically the set of points where this limit that we have established here exists, and basically at the domain of f prime of x is where we say that f has a derivative and it's differentiable. And a function that's differentiable at every point of its domain is a differentiable function. All right. So just in case this seems a bit out of nowhere, let's just go back and sort of motivate what the slope of a line at a certain point is, right? So let's say we have this random curve, right? We have a curve that goes like this, right? And then we know that the secant line between 2 points is basically a line that passes through these 2 points, right? And the way we calculate that is by basically finding the slope between these 2 points and then fitting a line through it. Now, we talked about tangent functions, and tangent functions are basically when the distance, so let's say this is x, and this is x plus some delta. When this delta tends to 0 is where we have a tangent function. So when this delta would tend to 0, we would get a line that's like this. Oh, that is wrong. A line something like this, right? And you know what? Let me just use a different color. We get, so if we were to draw a tangent line through x, it would look something like this, right? And that's basically when this delta right here goes towards 0, and that becomes the tangent line. And now that we have defined what derivative is, that's the slope of that tangent line is basically the derivative of this function f at point x. And we know we can find it through this limit notation. Now let's go through some examples. Okay, so let's find the derivative of f of x equals x cubed. So recall from earlier we defined that the derivative of a function at point x is f prime of x is equal to the limit as h tends to 0 f of x plus h minus f of h, or minus f of x divided by h, right? Now if we plug in what we have from this function, f of x is x cubed, right? So that would just become limit as h tends to 0, x plus h cubed minus x cubed divided by h. And then you can either remember the Pascal triangle or just know how the expansion of the cube function looks like. To expand this, and we'd get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed divided by h. Right, and then we would cancel these two out, and then we notice that every term has an h, and so that just we can take the h out too. So then we get limit as h tends to 0, 3x squared plus 3xh plus h squared, and then since the h is tending to 0, this two terms just become 0, and then we're just given is equal to 3x squared. So that means f prime of x is equal to 3x squared. And so that means if we're told to find the derivative of a of x cubed at maybe 0.1, right, then we just plug in 1 into our equation that we derived here, and we'd get the derivative of x cubed at x equals 1 is 3. What we've gotten here is a general solution for all values of x. All right. Now that we've gone through an example, there's also another alternate definition. So this is the alter definition of a derivative, and that's basically so this at a specific point A. So the derivative of f at point x equals a is f prime of a is equal to f of x minus f of a divided by x minus a. Limit the derivative of f prime of a is the limit as x tends to a of f of x minus f of a divided by x minus a. Now, to also get intuition about this, just remember sort of the example of the secant lines, right? Except instead of saying like a general point x, let's say we have some point x equals a, right? And this is our curve again, right? And there's another, like, this is sort of another point that's x, right? And then what we have here is at this point, this is q of x comma f of x, right, for a function q. And then this point is p a comma f of a, right? And if we were to do the slope, right, we'd get f of x minus f of a divided by x minus a, right? That would be our slope to this point. And we know as x approaches a, so that would mean that x gets closer and closer to here. So basically we're sampling points, like, we're going here, here, here. We're going all the way down to A, right? And then as we go down to A, we'll finally get the slope of the line that represents the tangent line. So it's very similar to our other definition, but this is for like a specific point. Right. So let's see how we can use this, apply this formula for like an example that applies this formula. So differentiate, right? Like when some prompts us differentiate, it's the same thing as finding the derivative. Differentiate f of x is equal to square root of x at point x equals a. So again, we're not using numbers because when we can solve things generally, it's probably much better, and you can probably apply to like specific points. So let's use the alternate definition. We know f prime of a is equal to limit as x tends to a, f of x minus f of a divided by x minus a. And then that's basically equal to limit x tends to a, square root of x minus square root of a over x minus a. So this limit is not the most trivial to solve, but there's a method where you multiply by the conjugate in the numerator. So we know that when we do this, multiply by the conjugate on both sides. In the numerator and denominator, because then it will just be like multiplying by 1. What happens is we get that is equal to limit as x tends to a, x minus a, because this is like the difference of squares equation, right? Where like 1 divided by 2, right? That because this becomes 1/2, right? Over x root x plus x root a minus a root x minus a root a. Right? And then if we were to do as x tends, oh wait, actually, we shouldn't have expanded the denominator because we have x minus a in the numerator, and then we have x minus a over square root of x plus square root of a, right? And this just cancels out, and then we're just left with limit as x tends to a over of 1 over square root of x plus square root of a, and then we plug in a for x, and that's just going to give us 1 over 2 root a, because you have root a plus root a after you plug in this, and that's going to give 2 root a, and that's our final answer. All right, so we looked at an example with the alternate definition and the regular definition, and so that's basically the derivative. You can basically find the derivative of any function through these two definitions. As we saw, we just have to be very careful with how we do our limits and know how to do various complex limits. Now, before I end, just some notation of how derivatives notation. So there's no like standard definition of how to represent a derivative. There's multiple ways. So whenever you have y prime or this prime, that means it's the derivative of the function y. Similarly, you can do dy over dx. That also means the derivative of y with respect to the variable x. So when you have like a function y is equal to f of x, the derivative of that can be shown as that. And then you can also actually do d over dx of f of x. So if there's a function f of x and you want to find the derivative of that function, right, you can represent it like this. And that's basically all the different sort of notations that you'll see to represent a derivative. Yeah, and that's basically it.